we're going to look at a very useful application of exponential functions, which is compound and continuous interest. Both when you borrow or when you invest money, you earn interest on the money that sits in the account. When you earn interest on previous interest, this is known as compound interest. The formula for computing compound interest is shown here on your screen, where A is your total amount of money or your balance at the conclusion of the interest compounding. Your P stands for principal, which is either the initial amount of money that you borrow or you invest. R is the interest rate. Make sure that you always change it to a decimal. N is the number of times that the interest compounds, or the number of compounding periods. So if your interest compounds monthly, your value would be 12. If it compounds weekly, it would be 52. And T is your time in years. Now, I want to point out that there is something known as continuous interest as well, where your interest is continuously compounding. This is a very similar formula where P, R, and T are the same thing, and E is your natural base, which we discussed is a constant. It's an irrational number of approximately 2.718. Let's look at an example. Mrs. Salisman invested $2,000 into an educational account for her daughter when she was an infant. The account has 5% interest rate. If Mrs. Salisman does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded? Well, let's look at if it's compounded quarterly, which means it's being compounded 4 times a year. So we're going to set up our initial equation where P is our principal. So our starting amount that she puts in the account is $2,000. Now, that will be multiplied by 1 plus your interest rate, which is 0.05, times the number of times it compounds each year, which is 4 when it's quarterly, raised to the 4 times the amount of years, 18. You can then put this into your calculator to see the amount of money you have after 18 years. So if it's not touched at all, you have $4,891.84 just by it sitting in the bank and earning interest on the previous interest, as well as the principal. So let's look at how much more money you would earn if this compounds monthly. So our scenario is pretty much the same here, except if it compounds monthly, our end value is 12, raised to the 12 times 18. And when my fractions get real ugly, I just leave them like this and just put it into the calculator so I don't round multiple times, because every time I round, my answer gets a little bit more wrong. So I get that A is approximately $4,910.02. So you earn more just by letting it compound more frequently. Let's check out what would change if we compounded daily. When I put this in, I get $4,918.90. So you should be seeing that the more frequent it compounds, your interest compounds, you will earn more money. Now, that's of course if you're earning interest. If you are paying interest, like you are on a mortgage, you're going to be paying more the more frequently it compounds. Now let's look at the same scenario and consider if it compounded continuously. So that's indicating that I'm going to use my continuous interest formula, where I'm using the natural base of E. So P times e to the RT, where P is my initial balance of $2,000, E raised to the rate, which is 0.05, times 18, or 2,000 times e to the 0.9, and that is $4,919.21 is how much you would earn if it compounded continuously, which you'll notice is really close to the 365 in this scenario, but you would notice a bigger difference if we were dealing with larger numbers.